Hi, my name is Rahman. So now I will present to you about our IDP project, which is Thermal-AIoT, real-time automated complementary diagnostic system. So I will proceed with problem statement. So now, humans rely on manual inspection base, which is vision base. So it is failed to detect internal biological change of heat, and also inaccurate classifications, delay hours, and also reduce crop quality. So we did this project to overcome the problem statement. So next, we continue to the objective. So first is to develop the thermal detection system using Raspberry Pi, DHT22, MLX90640 sensor. To apply the LCM feature extractions and machine learnings, SVM, RF, and also XGBoost for accurate reference classifications. Second objective is display real-time thermal heat map temperature and measure this status thoroughly on OLED screen. So we move to the flowchart. So we start with MLX90640 thermal camera. Then we go to capture the thermal image. So we check whether is thermal image data available. If yes, we continue to check the is data temperature and humidity available. If no, we will capture again. For the DHT22 sensor, we measure the temperature and humidity. So we check again whether there is data temperature or humidity available. If yes, we proceed to is the AI process complete. So if no, we capture again to MLX90640 thermal camera. So we start with Raspberry Pi and AI processing. We go to AI data processing and we check again, is AI process complete? So if yes, we continue to the ML classifications, which is SVM, RF, and also XGBoost. So if no, we go to AI data processing again. So we continue to the is classification done. If no, we go to AI process complete again. So if yes, we generate the result. After we generate the result, we will display on OLED. So it will check whether it's matured or over-matured.
To train our models, we first extracted 12 specific features from the thermal image. This included 7 statistical features like mean and standard deviation, and 5 GSM texture features such as energy and contrast. To ensure the best performance, we use 5-fold grid search civil to tune the hyperparameters for all 3 of our models. First, we tested the support vector machine SVM. This proved to be our most successful model, achieving the highest accuracy at 88.12%. Using a linear kernel, it separated the data beautifully with very few misclassifications. Next, we evaluate random forest. Using 100 trees, it performed very well and scored a close second with 87.13% accuracy. But it could not quite beat SVM. Finally, we tested XGBoost. With a learning rate of 0.01, it achieved 85.15% accuracy, making it the lowest performer of the 3 for this specific dataset. As a conclusion, comparing all 3, SVM was clearly the most effective at classifying our thermal data. Therefore, SVM was chosen as our final model. It was saved as best Okra SVM model.pkl and successfully deployed to our Raspberry Pi for the real-time Okra maturity.
Now we go to the accuracy. I want to show you how our 3 models AI perform. To test our system, we scan 101 okras, which is 50 good one and 51 overripe one. So look at the result. First is SVM. This was our best model. It scored the highest with 88% accuracy. Out of the 101 okras, it correctly guessed 46 good one and 43 overripe one. Next is random forest. It came in a very close second place, which is 87 accuracy. It also guessed 46 good okra, which is only missed one more override okra compared to the SVM model. So lastly, we have XGBoost. It got the lowest score out of the three, which is 80% accuracy. It correctly guessed 43 matched okra and 43 overripe okra. So the final result is SVM will get the most accurate and do the best job at catching the bad overripe okra. So based on our project, SVM is the perfect choice for our smart sorting machine. So now let's take a look at the confusion matrix for our two models. This slide visually break down exactly where each model succeed and where it made mistake total for our okra samples. So from the left, it is SVM, which is got highest accuracy at 88.12%. The middle one is the random forest. It perfectly matched SVM on the matched okras, also get 46 correct. And the right one is XGBoost, which is, you will notice that the top left yellow box is a bit darker here, so that it is only catch 43 over matched ones. So by comparing these matrices side by side, it is easy to see the winning pattern, which is SVM has the highest values in bright yellow diagonal boxes, which is the most reliable model to separate the good okra from the bad okra. So now is the visual of our system that actually sees through the thermal camera. This slide shows a real-time scan of two different okra that display as thermal heat map. On the left, we have adequate matched okra. At the top of image, you can see the live data from our DHT22 sensor show an ambient room temperature at 26.5. The color pattern here, the heat distribution is mostly dark purple and relatively uniform, meaning that the okra is retaining moisture evenly. So our system did calculate a lower mean value, and our SVM model correctly predict this as adequate matched okra. So now look at the right side, which is an overmatched okra. Here the room temperature is slightly higher at 32.3 Celsius, but the most important thing is the thermal pattern. So the patchy heat distribution happens because overripe okra becomes fibrous and loses moisture that cause it to trap and release heat differently. So it will predict it as overmatched. By translating these visual heat patterns into mathematical numbers, our localized AI system can instantly accurate sort the good okra and the bad one. On this slide, we did summarize our model performance and take a look inside the AI to see exactly how it makes its decision. So first, looking at the bar chart on the left, we can see a direct comparison of our three machine learning models. So SVM lead the pack with an highest accuracy, random forest is right behind, and XGBoost is the last one. This visual clearly confirms why we choose SVM as our final model for deployment. So now the chart on the right is very interesting, which is the future importance chart generated by our random forest model. It ranked our 12 extracted features to show us exactly which data points were the most helpful in telling the difference between a matched and overripe okra. As you can see, the number one most important feature by far is contrast, which is a GLCM texture features. The second most important features is standard deviation, which is statistical features that also measure how spread out the temperatures are. So this chart proves that our system isn't just making random guess, it is making smart decisions based on physical and thermal texture changes that happen inside the crop.
Okay, now I want to show you the simulation and the circuit connection in our project. So first thing first, we use the Raspberry Pi, MLX90640 thermal image camera, the DHT22 sensor temperature, and we use the power source. We use phone charger as power source and the display of the Raspberry Pi and then we connect with the laptop using VS Code.
So for our project, we did use Okra to get the sample dataset of our project. So we need to check whether it is adequate matured Okra or over matured Okra. So we want to check it by put it in front of the thermal image. So after we put it like 60 seconds, every 60 seconds, the result will generate at the face.
So now let us show you guys how we identify this okra, it is matured or over matured. On this display, it will show that this is over matured okra, which is ambient temperature 26.4 degrees Celsius, and it shows that humidity is 60.8%, and it shows the means met and also standard. Okay, so now we see that this is for adequate matured okra, which the ambient temperature 26.4 degrees Celsius and humidity 59%, and also it shows the mean, max, and also standard. But for our project, they have the limitation. The limitation is at the camera MLS 90640. We cannot put the okra far from the thermal camera because it will not get the real data set. So we need to put very close so we can get the real data set. Okay, our potential of commercialization is, our target user is commercial farmer and agricultural corporation. So we can see the market needs, because we need to detect the internal crop degradation before visible, and the product value is a low cost, non-destructive, and reduce labor cost. So the future improvement that we will do, we will add optical cameras and automated sorting line.
Our novelty and inventiveness of our project is Edge AI classification. We did use the LCM and multiple machine learning models, which is SVM, Random Forest, and XGBoost for highly accurate maturity detection. Our project is also a fully offline operation, which is process heavy thermal data locally, removing the need for cloud computing or Wi-Fi. Next is non-destructive scaling. It looks past the skin to measure through internal biological changes, which is moisture and texture of the fruit. Next is dynamic calibration. It is actively offset ambient room temperature to guarantee accurate thermal readings.